Hello, this is Concrete Path. Here we have the lecture for permeability in soils. Permeability in soils. Permeability in soils. Okay. So what's permeability? Permeability, we say that this is the ease with which the water flows through the soil. With which the water flows through the soil. Water flows through the soil. Okay. Now, this for permeability, the knowledge of permeability is helping us to assess the different properties of soil, and it helps us to assess what you call as its knowledge helps us to assess that what is the consolidation of soils, how much consolidation of soils. So we can write consolidation settlements of soils. So on the soil we would be having buildings, so I would say what is the settlement of buildings. We can write buildings are there. Design of filters, if you want to design the filters for your dams, embankments, etc. So to prevent the piping of those filters, to design of filters I would write prevent piping of those structures, prevent piping. Okay, and there are a few more terms we can assess from understanding the permeability. There is that hydraulic stability of structures, hydraulic stability of structures, soil masses. Okay, seepage, analysis of that seepage. We can get the what is the seepage through and below the structures, So that is the use of that permeability of soil. So that's actually how the water is flowing through the soil. So we have a law here that's given by Darcy. So that's your Darcy's law. So let's write Darcy's law. So what's saying here? We are going to talk about that soil. Let's take any general soil. That this is your soil. This is your soil mass. Let's take any two sections. Number 1, number 2 of length L. Let's say this difference between the two. This is your length of soil, or that's L. Okay, between two sections. I would say what is the if I talk about that, we have the concept of what you call as total energy head. Do you know that total energy head between at any point that's actually sum of three those heads. That's one of your head is velocity head. Second one is their pressure head. Third one is their datum head, elevation head. So the third one is their datum head. And for the Darcy's law, what is the assumption? What is the Darcy's in the Darcy's law? What is the assumption? We say your soil is fully saturated. Soil is fully saturated. Okay, we are talking about one dimensional flow, and velocity of the soil, velocity through the soil is actually negligible. Let's say that we say that your flow is actually a laminar flow. Velocity is less, so laminar flow is there. Velocity is less, laminar flow is there. If the velocity is less, we assume that velocity is less through the soil, and for that we are going to use laminar conditions. So at that time we say that this velocity head can be neglected. Velocity head can be neglected for your laminar flow condition. For a laminar flow condition, we can write here, because velocity is less, so that means we can talk about the total head. Total head is actually sum of now pressure head and datum head now. So we are going to talk about those. So in this analysis, we also call it as seepage analysis. So in this analysis, we are going to talk about the total head in terms of pressure head and datum head, because your laminar flow conditions are prevailing in the soil mass. So okay. So I would write what is the total head at the section A. If I keep any datum somewhere, let's keep the datum. Let's say that this is our datum. This is your datum. Let's say this is your datum. So I would say, what is the head here? What is the head here? if the datum is same, I'm going to say datum is same here. Let's say that datum is same. I would say that total head is actually difference of pressure head here. If I say here we have a total head of H1. Let's say this is your head 1, and at this location we are having head of H2, such that the flow is possible. If the flow is possible, I would write that if the flow is possible, if the flow is possible through soil, flow is possible through soil only from high head to low head, from high head to low head. So that means if the flow is possible from section 1 to section 2, there would be loss of head. There should be some loss of head. There should be some head difference between the two sections. There should be some head difference between the two sections. So that was that we can write delta H, or we can write delta head loss. That's your head loss. So there should be some head loss between the two sections, such that the flow is possible from one section to another section. So because the flow is there, and in this direction there is the soil, so soil is resisting that flow, so because of that there is loss of total head between the two sections. So I would say if the flow is possible between the two sections, there would be loss of head. And if I write that head in terms of head head loss by that length of the soil, in this is your head loss in the length of L of the soil. So this has occurred in length L. This head loss has occurred in length of L, length L of soil specimen. Okay, so that term head loss per unit length, we call it as hydraulic gradient, hydraulic gradient, hydraulic gradient, hydraulic gradient. So this is actually based on the concept of hydraulic gradient line, because we said that your velocity we are going to ignore. If I say that there is some hydraulic gradient line, somewhere we are having hydraulic gradient line between the 2 points. Let's say I have the hydraulic gradient line. So this is your hydraulic gradient line. So this is your HGL, we can write. This is your hydraulic gradient line. And from this we can get the slope. That's your head loss per unit line. That's your hydraulic gradient. Hydraulic gradient. Okay. That we also call it as seepage head. That we also call it as seepage head. Loss of head is actually seepage head, because the flow is possible from high head to low head. That's also called as seepage. Flow of water through the soil. We can write here. What is seepage? What is seepage? Seepage is also there. That's the flow of head, flow of water, flow of water from high head to low head, from high head to low head, to low head. So that's your seepage. Although that's also, we can say, your permeability is somewhat that it's permeability saying that we are going to pass the water through the soil, and your that's possible only because of seepage head. If there is flow, if the flow is possible, that would be only possible if there is a head difference between the two sections. So finally, if I talk about what's Darcy law now, so Darcy law takes the assumption that soil is fully saturated. 1D flow condition is prevailing. Velocity of the soil is less. That is, the laminar condition are present in the soil. So at that time we say their hydraulic gradient. Your velocity of the flow through the soil is actually proportional to hydraulic gradient. Is proportional to the hydraulic gradient. That's your Darcy law. Your velocity, that's somewhat in this fashion, that the in this part of the, if the velocity here was what you call as laminar condition, so in this condition we say your velocity is proportional to the hydraulic gradient. Velocity is proportional to the hydraulic gradient in this condition. After that we can have transitional phase and turbulent phase if the velocity is more. In this case velocity is less. So in this part velocity is less, so we are saying that that velocity is proportional to the hydraulic gradient. Now we need to remove that proportionality. So for that we have V equals to K times I. So your velocity of the flow, velocity of the flow, velocity of the flow is equals to some coefficient into your hydraulic gradient, hydraulic gradient, hydraulic gradient. And this K, we call it as coefficient of permeability, coefficient of permeability. So that K is actually coefficient of permeability, coefficient of permeability. Okay, so that would be given by that K equals to V by I. Can we see that? K equals to V by I. So that's actually, we would say this is actually velocity velocity of flow, velocity through the soil, or velocity of flow through soil under unit hydraulic gradient, under unit hydraulic gradient. So hydraulic gradient. So that's its units would be same as that of that of velocity. So this would be in meters per second. How much flow is there? How much flow is there? How much velocity is there through the soil? That would be actually permeability, coefficient of permeability. If the hydraulic gradient is unity. Okay. So that was your Darcy's law. Okay. We can also understand that in one more perspective, that one more way, that if you have the soil mass, if there is a soil mass, there is the area of the cross section of the soil mass. This is your area cross section of the soil mass, and there is any length of the soil mass L, and we are supplying the water. So there is flow of that, there is flow possible. That means we are supplying some water from one of the side, such that here we have some water level. Let's say this is your water level. Okay, from the other side we are maintaining a head difference between the two ends of the soil mass. So here we are having some head also, such that the final level is somewhere here. So here we can say that there is some difference of head between the two sides at this section 1 and at this section 2. I would say that there's some head difference, and there's some head difference of we can write this is your head difference of h. So that h has occurred in the length of L of the soil. So that h has occurred in the length of the soil L. So I would write based on the Darcy's law, that velocity would be proportional to hydraulic gradient, and that hydraulic gradient in this problem, we can say this is your k times your hydraulic gradient is head loss. This is your difference of the head between the two sections, head loss per unit length. So if we try to say there would be flow, there would be some flow. So some flow is there. So I would say, what is the flow? What's the value of that flow? So I would say, what is the value of flow? That would be given by continuity equation. That is Q equals to area into velocity. Q equals to area into velocity. If there is any cross section of that soil mass, there is this cross section of the soil mass, total area of the cross section. This is your area of the cross section A. Let's say this is your area of the cross section equals to A, and velocity is there, equals to V throughout the cross section. So your velocity V is actually velocity of the flow throughout the cross section. Velocity of the flow throughout the cross section, and that would be that we can equate with that we can write here also. Let's write that A times, let's substitute the value of V from the Darcy's law. So that is actually K times H by L. So your value of coefficient of permeability would be equals to K equals to, what is that? QL by AH. So your permeability value is equals to QL by AH. So what is the flow possible? How much flow is possible through the soil? That's equals to Q. And what is the area of the cross section? And what is the velocity through the entire cross section? And that would mean give me continuity. From the continuity, we can get this result for your coefficient of permeability. Okay. Now, if we say that this is not the actual scenario in the soil mass, this won't be the actual scenario in the soil mass. Let's see what's actual scenario in the soil mass. Let's try to get the cross section of the soil mass. I would say this is your cross section of the soil mass. What's present in the soil mass? If you cut the cross section of soil, I would say, what is the soil? What does the section look like? There would be some solids. There would be some solids present in the soil. So these are your soil solids. These are your soil solids. These are your soil solids. Can we say that? These are your soil solids. So solids is there. That means the flow won't be possible through the solids. Flow is not possible through the solids. Flow not possible through the solids. So that means we were saying that we are having that discharge of Q in that total area of the cross section A, and there is some velocity throughout the cross section. So that's not actually true. So your Darcy law, we can also say that your Darcy's law, Darcy assumes that it assumes that flow is through the entire cross section. Flow is through the entire cross section. Flow is through the entire cross section. But that is not true for the soil. That's not true for the soil. So we have to get the actual scenario what's happening. So I would say there we are having some volume of voids in the cross section, or we can write area of the voids. We can write there's some area of the voids in the cross section such that that is less than total area of the cross section. So from the voids only we will be having some flow. So from the voids only we will be having some flow. So this is the area of the voids. From the area of the voids we are having some flow. Flow is possible in the area of the voids, not through the soil solids. Can we say that? So we need to modify that equation. We need to modify that. So I would write your based on the continuity that this was throughout the cross section. This was talking about the throughout the cross section. So this was your area of the cross section, total area, gross area, and velocity was there for throughout the cross section, But that is not true. So if I write that equation, that discharge is not going to change, but the parameters are going to change. Let's see the parameters. I will write we are having some area of the voids through which the discharge is possible, and because of that there would be some velocity through the voids. There would be some velocity through the voids. Velocity through the voids. Velocity through the voids. We can write velocity through the voids. So such that your continuity is maintained. So Q has to be maintained. So discharge has to be maintained, but that means your A and V has to be replaced by actual scenario, that's area of the voids through which flow is possible and with some velocity through the voids. Can we say that? And so based on that we will write that your velocity, your actual what we write at your actual velocity would be area through the void, your velocity through the voids. Your actual velocity would be velocity through the voids. Velocity through the voids. Can we say that? Through the voids. Your actual velocity in the soil mass would be your velocity through the voids. Velocity through the voids, and that we call it as seepage velocity, through which water is going to seep. The water is going to seep through the voids only. So that we will write that seepage velocity. So that we denote by Vs. That we denote by V and S, Vs. That's your seepage velocity. So we can replace this one as area of the voids into seepage velocity. Area of the voids into seepage velocity. Okay. And this capital V, which was initially, which was we are assuming that this was through the entire cross section, and we call it as superficial velocity. Superficial velocity. This is not the actual velocity. Superficial velocity. This was talking about the entire cross section. That was velocity throughout the cross section. It was saying I am the velocity throughout the cross section. Throughout the cross section. But that's not actual true scenario. Okay. So we can have one of the equations here. Let's try to get one of the equations. I'll write here A into V is now equals to area velocity, area of the voids into seepage velocity. And if I multiply that total length of the specimen, we can get total volume of the soil mass. If I want to get the total volume of the soil mass, I would say take all the length, and this area cross section, that would give me total volume. Take all this cross section and total length L, so we can get what you call as total volume. So I would write this total LA is equals to total volume. This is the total volume of soil. And this is your velocity. Let's write it a little bit of curved. This is your velocity, and this is your volume of voids. Can we write this is your volume of voids? This is your volume of voids. This is your volume of voids for length of L. For length of L, we're having that some volume of voids. If we have some area for the voids and we multiply that length, we can get volume of voids. And there's some seepage velocity. And we know that volume of voids by volume of soil is equals to porosity. Do you know that? This is the porosity. So we can write that there's some porosity, there's some seepage velocity, and there's some superficial velocity. So we can write that your seepage velocity or actual velocity would be your superficial velocity by porosity. Can you write that? And we know that your porosity is also always less than 1, because you are having some volume of voids and volume of soil. So if volume of voids is there and soil is there, that means there's always possibility that porosity is less than 1 always. So that means we can write your seepage velocity is actually always greater than your superficial velocity. superficial velocity. Can we write that? Your seepage velocity is actually greater than always what you call as superficial velocity. And we have that equation of V equals to Ki. This was your coefficient of permeability corresponding to seepage velocity. Yeah, corresponding to superficial velocity. This was your coefficient of permeability corresponding at the rate of superficial velocity V. Now, if I write coefficient of percolation, we have one more term, that's coefficient of percolation. Okay, so that's given by actually that coefficient of permeability at the rate of superficial velocity divided by n porosity. So that's actually one more term for permeability. That's one more term for permeability, coefficient of percolation. Coefficient of percolation, and that would be always greater than coefficient of permeability at the rate of what you call as superficial velocity. So this one is your that seepage velocity would be always greater than superficial, yeah, seepage seepage velocity would be always greater than superficial velocity, and your coefficient of percolation would be always greater than coefficient of permeability. Okay. Now we say that we can now ignore for engineering practices. We say that we can take actual in terms of actual velocity. In terms of actual velocity, what you call as seepage velocity, we are going to still take that what you call as superficial velocity for calculations. We are still going to take that what you call as superficial velocity for calculations. We are not going to worry so much about that seepage velocity, Vs, actual velocity. We are going to take that superficial velocity for calculations. Okay. Now that was all about what you call as Darcy's law. Let's try to revise those. All of the stuff for your Darcy. So Darcy said that our soil should be saturated. Soil should be saturated. Uh, Soil should be saturated. That means once the soil pores are saturated with the soil, that water, then after that, once we are applying some water from the top, let's say from the top, we are allowing some top water, so that would be allowed to leave the soil, because soil pores are already saturated, so that would be collected from the bottom. Otherwise, once you try to perform that lab test, so let's say that you are performing test, so that would be some of the water would be now taken by the soil in order to get saturated. So your readings would get disturbed. You would say, what's happening with the soil? So I want that soil to be saturated. That's why here, this is one of the assumptions, that I want soil to be saturated fully. And for easy calculations, we say that we can talk about one-dimensional flow, and velocity of the flow is such that we are talking about the laminar conditions, such that your velocity is proportional to hydraulic gradient I. Okay, then we take those two sections. We say that if the flow is possible, it always happens from high head to low head. It always happens from high head to low head. So from the soil, if I want flow to happen, that would be under some hydraulic gradient. Under some hydraulic gradient of I equals to some head loss between the two sections divided by total length of that section. That is your head loss per unit length. And based on that, Darcy's law says that velocity proportional to hydraulic gradient, and we can have that coefficient of permeability here, K. So V equals to Ki. Then we say that if I take a cross section, if I try to take a cross section of the soil mass, I would say we can have some flow. We can have some flow of water that's under some head difference of H. So if I have that equation of Darcy, so that would give me some V equals to K times head loss by length L. And if I try to have the continuity, if I use the continuities, that's Q equals to AV equals to this one equals to this one, so we can get the value of K. And after that, we have the actual scenario that we are having in the cross section of the soil mass. We are having some solids, and from the solids, flow is not possible, and from the voids, flow would be possible, such that your actual area of the flow is less. That's actually area of the voids, and so through that we'd be having some velocity through the voids, and that we call it as seepage velocity, or that's your actual velocity. That's the actual velocity through the soil. And that when we equate that based on the continuity, we got this equation of your actual seepage velocity is actually superficial velocity divided by porosity, and that's always greater than seepage velocity, greater than superficial velocity. And similarly, that we have coefficient of percolation greater equals to K times by N. Okay, that was all we had talked about. Okay, so I would right now that this permeability is actually that is the flow, our right velocity of the flow. So your permeability is actually velocity of the flow under some hydraulic gradient. So that means its units is in meters per second. So if I talk about we're having sand, we're having some coarse sand, coarse gravel, that means we're having some gravel, we're having some sand, we're having silt, and we're having clay. So the value of the permeability is actually decreasing in as per the as per the what you call as size of the what you call as soils are decreasing. So your permeability is going to decrease as per the size is going to decrease. So for the clay, we say that your clay is some sort of impervious. We write that it's having almost a permeability very less, that we write it as impervious soil, and its value is somewhere 10 to the power minus 6 centimeters per second. Less than that, your value of K is less than 10 to the power minus 6 centimeters per second. That means once the soil mass is fully saturated, now you are applying that water to pass through the soil. Now it would in 1 second it would pass how much centimeters? 10 to the power minus 6 centimeters. So if you apply that water, it would reach this much amount of centimeters in 1 second. That's your permeability. And for that, what you call as gravel and sand, we call it them as pervious soils. These are your pervious soil. And for the slit we write silt is your little bit of pervious, so we write it as slightly pervious. Slightly pervious. Okay. Now, once this coefficient of permeability is there, we need to determine this value. What is the value of that K? So coefficient of permeability has to be determined. So for that, we have different approaches. So let's go for that determination of permeability. Coefficient of permeability. Determination of coefficient of permeability. Coefficient of permeability. That is the K. How do you determine this? So for the determination of that value of K, we have four ways we can get this. We have four different ways we can have this value. So first one is that we can have, that's the lab methods. Lab methods we can have. Second one is there, that's field methods. Field methods. Third one is there because of some equations, because of some relations between other stuff. So relational, we can write equations are there. Equations based on other properties of the soil, we can relate those with your permeability, so we can get the that permeability value. That is the indirect. This means that this is your indirect way, indirectly. Or we can ignore this part, so we can have relational or equations. After that, there's fourth method. That's what you call as capillarity permeability test. Capillarity permeability test. Permeability test. Permeability test. So from the lab method also, we have two different kinds of methods. One is your constant head permeability test. Constant head permeability test. And second one would be falling head permeability test. Okay. And in the field methods we are having that we are performing the test in the field. That's we are having those pumping wells, and we are extracting water from the wells. That's your pumping out test. And next one is their pumping in test. Pumping in test. So in these, we are not going to touch those. These are your concepts for your hydrology. I would say from these we are having two equations. One is your Thames equations. One is your Dupit's equations. To calculate that your permeability is related to their discharge. So from that we can have that equations. So we say that your pumping out test, it talks it there's influence, zone of influence. We call that zone of influence. A term is there that we call it as zone of influence of that pumping well. So there's some wells, from that we are extracting that what you call as water. So that's called as yield of well. Yield of well. Yield of well. So in the pumping out test, there is more zone of influence. More zone of influence is there. So that means the value of K we get, that's talking about a general value. So that's a better value. Better value of that K we get. Better value, or we can write K is better. or we can say it gives a general value of K for a large area of that around that pumping well. And for the pumping in test, it talks about a small area. Its zone of influence is a small area, so your permeability value we got, this is only for a limited area, for a limited value of that area. Okay. Now for those equations relations, we can have different equations, different formulae we have. One of the relation is Kozny-Korman is there. One more is there that we have about the what you call as consolidation. Consolidation relation is there. So that we are going to see. We are going to see those also later. So final one is there, that is capillarity permeability test. So this is the one method in which we can keep the soil unsaturated also. We can keep the soil unsaturated also, and we can also get the permeability value. Even the soil is unsaturated, but we can still get the value of K in this method, capillarity permeability method test. So let's go for your first kind of approach, that's lab methods. Let's lab methods, and from that we are going to talk about constant head permeability test. Constant head permeability test. Okay, constant head permeability test. Let's talk about constant head permeability test. So here the name suggests that we are maintaining constant head. We are maintaining constant head. Let's say that we are maintaining constant head. Let's say that head is somewhere here, and this head is maintained constant, and we are having some soil mass. We are having some soil mass also. Let's try to make the entire picture of that. Water is flowing from the top tank. From the top tank it's flowing, and there's some attachment assembly, so that we're having some soil mass in that structure. So let's say that soil mass is in this part. This is your soil mass. This is your soil mass. Soil mass of length L. Soil mass of length L. After that we're having from the bottom also, we're having the what you can say, that assembly such that we're allowing the water to leave. Let's say that we're having some assembly such that water is going to leave. Water is going to leave. Okay. Now if I have that manometer readings, I would write here we're having some head. Let's say we're having some head of H. We're having some head of H. Some head is there. Some head is there. Okay. Let's say that there's some head H1. Let's say that there's some head of H. Okay. And from the bottom of soil we can say there's some one more head, such that there is some head difference. So we can write this is H1, this is H2. Manometric head levels. And I would say that what is the head difference between the two sections? What is the head difference between the two sections? I would write there's some head difference between the two sections, and I can write that as some head, small h. Small h is there. So that is the head difference. Head difference of small h. Head difference of small h. Okay. Now I would say if the flow is possible, there is some Q, there is some capital Q. Right, let's write that as capital Q. So if the flow is possible from one end to another end, so I would say that your loss of your head loss should be there. Your head loss should be there. If the flow is possible, it would only possible. Flow is only possible if there is head difference between the two sections. So that head difference we have written that as H. That is also seepage head. That's also equals to seepage head. Seepage head. Okay. Now I would write, based on the name of the topic, it's saying we have to maintain the constant head. We have to maintain the constant head. How can you maintain the constant head? If your level initial value of the level is somewhere here, after some time t, your level would be somewhere here. So there would be change of there would be change of head. There is change of head. That means initially there was head of h1 for your length of L. So your hydraulic gradient was I1. At that time your velocity would be V1 and your discharge would be Q1. And at the time t2, your head difference is h2. your hydraulic gradient is I2, velocity V2, Q as Q2, so different values we can get. But we want to ensure that we are getting single value of K. So for that we have to maintain the constant head. We are maintaining constant head. So for that we have to supply some water from the top also. We have to supply some water from the top also. Okay, we have to supply some water from the top. So there should be some assembly such that water level is maintained from the top. So there should be some supply from the top. So constant, I would write constant head maintained by some supply. Constant head maintained because of some supply. Let's say there is some supply of water. Supply is there. There is some supply of water such that your head is maintained constant between those two sections. Okay. Now if I try to have that equation of Darcy, what is Darcy there? V equals to K times I equals to K into head loss of H for the length of soil equals to L. And if I use the continuity, that Q equals to area into velocity, and we are going to talk about that superficial velocity that was not actual, and still we are using that in calculations. So total area of the cross section and your velocity of that cross what you call as flow throughout the cross section, that is equals to K. Yeah, that's actually equals to A times your velocity of kh by L. So your permeability value of K can be equals to Q times L by AH. Q times AL by A. QL by AH. So this is one of the ways we can say. And if I try to keep the container at the bottom, so let's say that there is some container and initially the water level was 0. So I would write we are getting some volume of V, in time t. Let us collect a volume of V in time t in that container. So I would write based on the continuity, I would write your volume of V in time t has been attained because there is some discharge of Q. Equals to what was the equation? Your KAH by L. Can we write that? KAH by L from this relation? KH by L. So I would write your value of K can be also solved in this way, that we are having VL by hat. So that's one more way we can write it. VL by hat, or we can write QL by AH. So in this way we have to substitute that value of Q as a value of velocity by that volume by time, and then we have L by AH. So that's the equation for your coefficient of permeability for your constant head permeability test. So this one, actually we are performing this test for your soils that are highly pervious, such that coarse sand is there, gravel is there. So for those kinds of soils, we are going to use that constant head permeability test. So for coarse soils, we can write coarse soil, because permeability is more. If you want to keep that, if you don't want to maintain the constant supply, that means at time t equals to 0 there was some level, and at time t equals to 5 seconds the water level has decreased to some value here. So it would give me exact analysis to perform. So for those soils there is more pervious nature of the soil, so I would prefer that constant head. Based on the constant head, I am performing that test, constant head permeability test. Let's take one problem for understanding this method. Let's take one problem. So we have coarse sand. Sample of height. Height of the sample is, let's write that height of the sample is L, equals to 20 centimeters. 20 centimeter sample, and area of the cross section of the sample. Is such that we're having some diameter of that. So we are having the diameter of the sample as 8 centimeters. That means it's some cylindrical sample. Is there. 8 centimeter diameter of the soil sample, and some height of 20 centimeters. Okay. This is your core sample. After that, core soil sample. After that, we are having water flow at constant head. Water flows at constant head. So it's saying that we are having constant permeability test, constant head permeability test. Constant head, how much? Of 1 meter for 15 minutes. So the test is performed for 15 minutes, and we have maintained the head difference of 1 meters between the two sections of that length. Here we are having some head 1 h1, and here we are having h2, such that the head difference here is h equals to 1 meters, and this test is performed for 15 minutes. And we say that how much water we have collected from the bottom. From the bottom we have collected how much water? We say we have collected how much water from the bottom. From the bottom mass of the discharge water found. Mass of discharge water found was equals to 1.2 kgs, and we need to get the permeability of soil sample. Get the permeability of soil, coefficient of permeability of the soil. So we have the equation that if this is constant head permeability test, so we can write the equation that uh, K equals to VL by hat. K equals to VL by hat from the relation that Q equals to KIA, and your Q by T is actually V. So we can write this equation. Your volume collected is actually Q by T, and that's actually KIA by T. So we write that K into I. I is your hydraulic gradient of H per unit length of L, and your area of the cross section of the soil sample is A, and in time T. So we can get the equation for your K, VL by hat, VL by hat. So let's try to get the values. Let's try to substitute the values. Let's try to substitute those values. So we are having that K equals to V. What is the volume of the soil mass? Can you get the volume? We are collecting this mass of this discharge water was to 1.2 kgs. From that, can you get the volume of water? What is the volume of water? Can you tell me? What is the volume of water collected? So that would be given by volume of water equals to mass of water by density of water. So I would write 1.2 kgs by what is the volume? What is the density of the water? Is that 1200? Is that 100 kgs? Is that 1000 kgs per meter second per meter cube? 1000 kgs per meter cube. So from that we can get the volume of water. Your volume of water is coming out to be equals to 1200 cc, 1200 cc centimeter cube. So we are getting this volume of 1200 centimeter cube into that length of L, height of L, that's actually sand sample height, 20 centimeters, divided by your head difference H. Your head difference of H, 1 meter, 1 meter, that is 100 centimeters, into that area of the cross section of the area of that sample, pi by 4 into 8 square centimeters square, into that time of t in the seconds. Your time of t in the seconds, how much is that? 15 minutes. So 15 minutes would be 15 minutes into 90. Yeah, 15 into 60, that's this much amount of seconds, that's 900 seconds. So from that, get the value of K permeability equals to 5.306 10 to the power minus 3 centimeters per second. 10 to the power minus 3. So since this is sand, so our value is more as compared to the value of clay, because the value of clay was in the order of 10 to the power minus 6 centimeter per second. So we are having more value here for sand. Okay, so let's go for the second method. That's what you call as falling head permeability test. Falling head permeability test. Permeability, falling head permeability test. Falling head permeability test. Okay. This we also call it as variable head. Variable head or falling head permeability test. Falling head variable, falling head permeability test or variable head permeability test. Okay. So in this case, we are going to have that what you call as we won't maintain the from the top container. We are not going to maintain the constant supply. We are not going to maintain the constant head. So in that case, we are going to have that variable head. So let's say that we are having that from the top. We are having what you call as a standpipe is there. This is your standpipe. We call it as a standpipe of area cross section. There's some area of the cross section of the pipe is A, area cross section, area of the cross section. This small a, okay, and initially the water level is somewhere here. Let's say that somewhere here initially there's water. Let's write that there's some water at time t equals to 0. We're having this water level here somewhere, and the assembly of that, this is your assembly. So from the bottom we are maintaining constant head. From the bottom we are maintaining constant level such that we can keep that as the datum. So this is your let's say that at the bottom side we are maintaining a constant head level. Let's say that this level we are going to maintain constant level we are going to maintain here. So this we can say this is your container that we call it as constant head chamber. Constant head chamber. So this is regulating the water such that your head at this location is going to remain same fixed such that we can keep it as a datum. So we are going to keep this value here as a datum. This section as a datum value, datum section. Okay. Now from the top we are not supplying any. There is no supply from the top. There is no supply. No supply. That means we are not supplying water from the top. Let's have the clay sample. Let's have the soil sample. Let's say soil sample is this one. This is your soil sample of length L. This is your soil sample of length L. Now initially from the top, your head difference between that datum and that initial level of water. Let's say that was let's take that value. Initially that was H1 at time T1. Let's say that initially we are having this head of H1 at time T1, and after some time T, our level is somewhere here. After some time T, we are having some level of what you call as different value of H, that is H2. After some time T2. So this is your our right your H2 level at time T2. Head to difference at time T2, and initially it was head of H1 at time T1. So because the head is varying with the time, so we had to integrate. We can write here because head is varying. That means your I would vary. I varies because after that their velocity would vary, discharge would vary. So for that I had to integrate. That means we have to integrate. Now we need to take any at any particular time of t. We need to take at any particular value of time time t. Let's take any time t. Let's take the level somewhere here. Let's say this was your level at any time t. This was your level at any time t. Let's have that. Let's have that level also. So this is your level. That's we can write h at time t. So h, this is the head level difference between the two sections. This is your h at any time t. Now at that time t, we are going to now increase the time by small differential element of time dt. So we would say your fall of that water level from in the standpipe would be some dh. So there is fall of water level by some dh in some small time of dt. So we can have that small dh. Let's say small dh is there. Let's say small dh is there. Small fall of height is there. Small fall of height is there. Small fall of height is there. Dh falls in time dt. So dh falls in time dt. So can I write that dh fall of that height in time dt. So we need to say that your let's make the I would say let's have the fall of height. Let's have the fall of height in the standpipe, how much we're saying we're going to take dH in time dt. Uh, so I would write the equation. Then I would say, what is the volume that has fallen? What is the volume of that segment? What is the volume of that fall? So volume of that fall is actually, in that time t we are having some volume of the volume lost. I would write volume fall in that time dt is actually your area of the cross section for your standpipe, your area of the cross section for your standpipe into that small height of dh. So that's your volume fall in small time dt. So that should be maintained because of the continuity. That should be supplied from the soil by some discharge of q, and so that should be supplied from the soil by some discharge of q. So because this is fall, we are going to keep it negative. Otherwise, your final value would be in negative condition. So I would write, after that we can write your we can write there's fall of. So applying continuity equations, continuity equation. I would write that your volume falls volume falls by some v small volume falls, that is equals to small dv from standpipe in small time dt. So that should be equals to some discharge through the soil, through the soil in that time small dt, discharge through the soil in small time dt by the continuity. Can we write? So your volume falls by how much? Your volume falls in the standpipe by how much? So your dh into area of the pipe, area of the cross section of the pipe, that's small a, into that height of dh. So that's your volume. So I would write your fall of volume is actually minus times your area of that what you call as standpipe into the small height of fall, that is small dh, in time small dt. So that should be equals to the discharge through the soil. So discharge through the soil, that we can get from the what you call as Darcy's law. That we can get from the Darcy's law. We had the equation for your Darcy's law. We had the equation for your Darcy's law. We have the equation for your Darcy's law. That's your QIA. QIA. Can you write that? And I would write your Q. Your K is there, okay, but your head is there. But head is varying, but because hydraulic head is varying, so we had to take those critical locations. We had to take those critical locations. We had to take those critical locations. I would write your head loss at any time. Your head loss at that time. I am talking about the condition when height of the soil was height of that what you call as level was h. So we're talking about this condition. After that, there was some small increase of time dt. So we're going to take at that particular instant. So initially at that time we're having some height of h. So at that time we're going to take that hydraulic gradient at that time t. So I would write your head difference was h for the length of soil equals to L, and your area of the cross section is A. Now because your hydraulic gradient is varying, because I varies, so we need to take what you call as, we have to integrate a total equation. We have to integrate the equation now. Let's try to integrate the equation. Let's try to integrate this equation. Okay. Okay. So that means we are going to write minus times A dH by dt, yeah, equals to your final value of K H by L into A. So I can simplify the equation. I can simplify those equations. Let's keep that dH by H in one side, and all other stuff, the constant values, we can keep those parameters from the other side. Let's say those we are having this value of K, we are having the value of A, we are having the value of L, we're having one more part that's small a. So let's keep this negative also from the side, and we're having one more thing, that is your small dt. Small dt is there also. So we are going to integrate this equation now. Let's try to integrate this equation now. Integrate, because your variable is that height. What is the height of that? And that is your variable, and your time time is also variable, and height of that water in the standpipe, that is variable. So we are going to integrate those terms in order to get the value of permeability of the soil. Permeability of soil. So I would write, I want to go from a height of h1 to some height of h2, from time t1 to some time t2. Okay, so these were my initial setup conditions, that at any time t1 we're having some height of h1 difference between the two sections, and there is some height of h2 at any time t2 between the two sections, and at any critical time our height was h at any time t. So we had this datum. So from that we are having some difference of head difference h. So that's varying with time. So we're going to have that integration of that. So let's solve it. So we can solve it further. Finally, I would write your minus times ln of h2 by h1 equals to ka by al into time t2 minus t1. Okay. Now we can get the value of k. 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 So value of k would be some al by some a into t into some ln of h1 by h2. Some ln of h1 by h2. So that's the final equation for permeability of that soil. That would be equals to area of the standpipe, area of the standpipe, area of the standpipe, A times length of that sample, length of the soil sample, or we can write height of the soil sample, height of the soil sample, into area of the cross section, area cross section of that sample, soil sample, A, and your time. So t is your actual value of that is talking about the head difference. Where since we have the limit here, we have h1 by h2. That's talking about the height h1 and h2. So that would be corresponding to some time t2 minus t1 interval. So this is the interval when height head difference was h2 and h1 interval. I can write this is the time interval between when standpipe water level from the datum was h2 and h1 and h2 we can write. Okay, that is the difference of the two times. That is the time interval that would be given to you. That would be given to you. Okay, so final solution is there. We can also call it as, we can keep it in this way, that al by at and log of h1 by h2. But you can keep this equation, that's derived equation, we can use that. We would be using that. And this method, since your head is falling, so this method is preferable for soils that where the permeability is less. So this method is going to be used for the soils where permeability is less, like that of clay, like that of clay, like that of clay. So this would be used for your clay soils. Clay soils. We'll be using this one as for your clay soils, fine soils, fine grain soils. We can write undisturbed fine grain soils, undisturbed fine grain soils. Okay. So we can mention here, this is the test performed for undisturbed fine grained soils. We have seen that by disturbing your structure of that, clay gets changed, your structure gets changed, so properties gets changed for your fine grained soils on remolding. So that means we need to perform, if I want to assess the permeability of your field soil, so I want to get that soil into the lab without remolding that soil, such that I can get some approximate value of approximate actual value of what you call as fine grained soil permeability, fine grained soil. So that's why it's performed for undisturbed soil sample of fine grained soils. Okay. So finally, I would write, we derive two equations for your soil coefficient of permeability. One is your constant head method, and second one is your falling head method. So from the first one, we get permeability value of VL by head, or we can also say that QL by AH. So second one is there, K equals to AL by AT and ln of H1 by H2. Let's go for problem 1 related to variable head falling head method. Let's take the first one. So this one is your simple one. This method, this problem number 1 is very easy. Based on the based on the formula directly we can get. We have performed falling head test, falling head permeability test. Okay, and so your sample height 12.2 centimeter height. Area of the cross section of that sample is how much? 44.41 centimeters square. And water level in the standpipe dropped from height of H1 equals to 75 centimeters to height of H2 equals to 24.7 centimeters in how much time? In 15 minutes. So get the value of permeability. If the data for your standpipe, area cross section of that standpipe, I will write your diameter of that standpipe is how much? That is 6.25 millimeters. 6.25 millimeters. So we are having that falling head permeability test. There is some diameter of that standpipe. After we are having some soil sample of L equals to 12.2 centimeters, and water is flowing from the bottom, and we are maintaining the water head, what you call as constant level at the bottom by some chamber, constant head chamber. This is constant head chamber, and initially the head difference was how much? 75 centimeters. After that, at any time t equals to 15 minutes, we're having the head difference now only 24.7 centimeters. Now we need to say what is the permeability of that soil. We have the equation, get the answer. We have the equation, that's AL by AT ln of H1 by H2. So you need to substitute those values in order to get the equation, in order to get the final value. I would write here pi by 4 into 6.25. This one is your in millimeters. We want to keep all the, because all the data is in terms of centimeters. You can see all the data is centimeters, so we can keep this data also in centimeters. So we can substitute that 0.625. We can write 0.625. 0.625 square centimeter square into length of L. Your length of L, that's the height of sample. Your sample of is having that height of L equals to 12.2 centimeters, and divided by the area of the cross section of that sample, 44.41 centimeters square. Okay. After that, we are having that time interval between the two those head differences. So their time interval is actually 15 minutes. 15 into 60 seconds. That's your 15 minutes, and that ln of H1 by H2. Initially the height was 75 centimeters, and finally I am going for the height of 24.7 centimeters in the time interval of 15 minutes. So from that, get the value of what you call as K. K equals to 1.04 10 to the power minus 4 centimeters per second. Let's go for number 2. Let's go for number 2. Number 2 problem for your variable head permeability test, falling head permeability test. Okay, so we are having silty clay sample is there, and length of that sample, height of that sample is 15 centimeter long. Diameter of that sample is 9.8 centimeters, and diameter for your standpipe is actually how much? 0.75 centimeters. 0.75 centimeters. 7.5 millimeters. Okay. Water level in the standpipe was observed to fall from. Okay, right. Water level in standpipe was observed to fall from 60 centimeters to 45 centimeters in time t 12 minutes. In 12 minutes, the fall of that height is 60 centimeter to 45 centimeters. That is the 15 centimeter difference. Okay, now we need to determine number one, get the value of get the value of get the value of permeability in meters per day. Get the height of water. Get the height of water in the standpipe after 20 minutes. After 20 minutes. Number three, time required time required for water level to drop to 10 centimeters. Okay, we have the equation. What is the equation? AL by AT ln H1 by H2. This is the equation we have. So for the first part of the problem, we can get the solution that K equals to area of that what you call as standpipe pi by 4 0.75 square centimeter square divided by the area of the that soil sample pi by 4 9.8 square centimeter square. Can we say that? Okay. After that, there is length of the sample 15 centimeter long divided by the time interval between the two those readings. Time interval, what was the time interval? 12 minutes. So we can add 12 minutes into 60 seconds. And what is the ln of H1 by H2? That is 60 by 45. So that is the answer for your problem. That is K equals to some value. K equals to some value. So once I got the value, I can get the value in centimeters per second. Let me calculate the value. That's 0.75 square into 15 divided by 720 divided by 9.8 square. How much is that? Into the ln of 60 by 45 into 10 power 5. So that's 3.51 10 to power minus 5 centimeters per second. And in terms of meters per day, I would write that we're having how much meters we're having in 1 centimeter. I would write 1 by 100, or we can write 10 to power minus 2 meters in 1 centimeter. And we have this seconds. How much days we are having in 1 second? We're having 86400 seconds per day. We're having this much amount of seconds per day. So finally we can get the answer in this way. So multiply that 86400 and divide by that divide by that 10 to the power 7. That is 0.03. Is that 0.03 meters per day? 0.03 meters per day. Your value of K is 0.03 meters per day. Okay, for your silty clay sample. So we got the first part. Now I would write for calculating all of the data. We would say that your parameters that are going to remain fixed. We are going to see those values. I would write permeability is not going to change. Your area of the standpipe is not going to change. Your length of the sample is not going to change. Your area of the soil sample is not going to change. Only the parameters that are varying. We also saw that during the derivation. We're having that derivation of dH by h, and we're having that some value of those constants. We have already talked about that. Let me have that actual one. So dH by h, that was your k into a by al, and there was some dt. So your variable is actually which one of these is variable. So your variable is only time and your height in the standpipe. So your variables are only for the solution of the other two datas. I would write variable is only time, variable is t, and variable is height. So we can ignore all that stuff. So we can ignore this part. I can write we have this relation. Now. We can write at any time. We can use this equation now. Now for all other data. Let's see how we are going to use that part only, because all other data will get cancelled if you try to use that equation for different different time intervals and different heights. All other data is going to get cancelled. So finally we have that all that variable part is there that's left. That would be this part. Okay, let's go for the part number 2, where we need to get the height of water after 20 minutes. We need to get the height of water in this standpipe after 20 minutes. Now it does not say after 20 minutes that whether from the start or whether from the point when it has already reached 45 centimeters. Let's see the diagram. Let's see the diagram. This was your standpipe. Initially the height was 60 centimeters. Initially 60 centimeters. After that it has reached to 45 centimeters only. In time interval of how much? In time of 15 minutes. That was given to us 15 minutes. Yeah, in 12 minutes. That was given to us in 12 minutes. This fall is in 12 minutes. 12 minutes. Now it's saying that get the height of water in the standpipe after 20 minutes. Now we can solve two different conditions. That either we can solve it from this condition that after 12 minutes has passed. After 12 minutes has passed, we are going to take next 20 minutes. Next 20 minutes, then we are going to see what is the level somewhere here. Some H3 we are going to calculate. Or after that we are going to say that from the start we are going to take that 20 minutes. We would say where is the level somewhere here, H4. So we would solve for two different conditions. Let's take the first condition. We can write for the first condition we can write uh, for another 20 minutes. Let's try that solution. Let's say that H3 is that what we call it, height of water in the standpipe after another after another 20 minutes. So we would write that equation. We have the equation that 1 by T is equals to ln 1 by T of ln H1 by H2 is equals to 1 by T of ln H1 by H2. So if I have those variables now, I would say initially I was having that H1 by H2. So I can substitute those values of H1 and H2 here. Let me substitute those values in the time interval of that 12 centimeters, 12 minutes. Let me substitute that value. This was your 720 seconds, and ln of initial value was 60 to 45. 60 to 45. This is your H1. This is your H2. And I have already derived the value of K based on this result. So I would be using that same stuff for calculating the value of H3 now. I would calculate now the value of H3. So H3, I can write now this would be H2 and this would be H3, because I am calculating after another 20 minutes. After 20 minutes, another 20 minutes means that means at that time T. So another means here, another means that once it has reached to this level of H2, once it had reached to the level of H2, after that we are going to take 20 minutes more. So I would say your initial condition for that is actually your initial value of height is actually 45 and final value is H3. So I need to calculate that value of H3 in that time interval of another 20 minutes. So I can write here we have another 20 minutes. We have another 20 minutes and ln of some height of H2, that's 45 centimeters divided by height of H3. And from that I can get the height of H3 in the standpipe. How much is that? Height H3. So that's 27.86 centimeters. 27.86 centimeters. Now, if I try to calculate that same problem for 20 minutes, but from the start, So let me write H4 is height of water in the standpipe. In the standpipe, it's one more solution for that same kind of problem. Part two. Uh, After 20 minutes. From the start. So this is by the statement where we are going to change all that stuff from the start. We're writing here, and in the first problem we write from and after another 20 minutes. uh, that means 12 minutes has already passed. These 12 minutes has been already passed. After that we are going to take next 20 minutes. This is your next 20 minutes, but in this problem we are going to take all those 20 minutes but from the start, time t equals to 0. So I would say from the start, what was the height of H1? What was the height of H1? That was 60. So if I use the same equation here, I would write your uh, next 20 minutes, your what do you call as 20 minutes from the start That's actually 20 into 60 seconds into ln of height of h1, because I'm going from the start. I'm going from the start and I need to go for the height of h4. Okay, this is very very important here. And initially the condition was given to me that ln of 60 by 45. This was given to me. I'm going to use the same part here. Let me check the value for this condition. So here I'm going to substitute the value of h1 equals to 60 seconds, because I am calculating from the start. I am calculating from the start here. So I can get the value of h4 equals to, you can simplify it. Let's say you got some of the answer, then we had to apply that law e to the power of that answer. Finally you can get the answer for it. You can check that. Okay, so finally you can get the solution. Let's say that you got one of the solution in this way. Let me have that one of the solution. So once you solve for this value and this value and this ln of that value, finally you would get ln of h1 by, we can write this one is 60 by h4 is equals to some answer. And then finally I would write h4 is equals to 60 by 60 by e to the power answer. Can you write it in this way? Let me try to get the answer. Let's say that you get some answer of that's 720 divided by 1200. Can write in this way that that's 1 by 720 into 20 into 60 into ln of 60 by 45. So we got this value here. We got this value of 0.4795, and after that we can write your we can write it in this way. Now we would say your 60 by h4 is equals to e to the power 0.4795. So we can write e to the power of this answer. So that's 1.6152. So we can get h4 equals to that divided by that answer, 60 by that answer, 37.14, 37.14, 37.14, 37.14 centimeters. This is the solution for that part. Let's try to get that again. So we are getting two different values of height, but because the condition has been changed in the first part, I said that after 20 minutes, but from the after next 20 minutes, after another 20 minutes, from the data that was given to you. Let's see that again. So this was your standpipe. This was your standpipe, and there was some assembly. Let's say this was your assembly, and there was some level. This is your datum. Initially, from the datum, what was the level? From the datum, this was your initial level. This was your initial level of that water in the standpipe. This was your h1. h1 equals to 60 minutes, 60 centimeters, and time t equals to 0. And after time interval of 12 minutes, water level was somewhere here. So this was your height 45, 45 at time equals to 12 minutes. Now the problem is saying that get the value of height in the sample, height in the standpipe after 20 minutes. So first of the part I said that if I calculate for another 20 minutes, that's I'm going to now make the start from this point. So the start is going to be taken from this point. So there would be some fall of height such that the final value is somewhere here. So that's the value of h3 after next 20 minutes. So in that condition, I have to say that my value of h1 for calculating that one by time because my time interval is from the height of h2 to h3, because my time interval of 20 minutes is that we are talking about next 20 minutes, that would be from interval of h2 to h3. So in that condition, I have to write 1 by 20 minutes of ln of height of h2 by h3 is equals to the basic one that was given to us, ln of 60 by 45. Okay, 60 by 45. That was given to us. That is h1 by h2. Now, if I now keep the value of time from the start, if I say that I want to calculate from time t equals to 0 to time t equals to 20 minutes, my origin would now be from the start. So let's say that my height is somewhere at h4. Let's say the fall of height is somewhat in this way such that your value is only h4 now. Your h4 is only there, h4 at time t equals to 20 from the start. So my equation becomes 1 by 20. That's your time interval between the two conditions of h1 by h4, and one more condition was 1 by 12 of ln of h1 by h2. So that's why we have these two different equations. I hope you are getting the solution. Let's go for the third part. Third part of the problem. Third part of the problem is there. We need to calculate that time required for water level to drop to 10 centimeters. So for this part also we can solve in two different ways. For this part also we can solve it for two different ways. If I say that my height should be now only 10 centimeters, but it is from the start. If I try to calculate from the start how much time it would require, it would take me from the start to reach this level of 10 centimeters. So from the start, how much time it would take me to reach this level of 10 centimeters? So let's try to get the final part of the problem. So let's see that your initial height was 60, h2 was 45, and I want only 10 centimeters now. Such that this is only 10 centimeters. Such that this is your final 10 centimeters. So it would take from the origin, it would take some time from t equals to 0 to time t equals to that answer we need to calculate. And one more approach is that if once I have calculated for time t equals to 12 seconds, now from that time I can solve further that what is the time taken from t from 12. What is the time taken from 12 minutes to some time such that your final height is also 10 centimeters. So we have to do two different solutions for that answer, for that problem again. Let's take that condition. I would write from the start. If I want to calculate from the start, so if I want to calculate from the start, I would write your 1 by time t. So t is from start. I would write t is from start, time interval from start. So that's from 0 to time t. So I would write 1 by t and ln of h1 by h. That's your h5. h1 by h5 equals to 1 by 12 minutes. That was given to us 1 by 12 minutes from ln of 60 to 45. This is from the problem that was given to us. Now from that I would say what is the value of h1, because we are talking about from the start. So h1 is equals to 60, and your t is we need to calculate, and your h5, how much is the h5? So that's given in this problem, that's 10 centimeters. We need h is equals to h5 equals to 10 centimeters. So I can solve that 1 by t equals to 1 by t of ln of 60 by 10 equals to 1 by 12 minutes, and ln of 60 by 45. So I can get the solution in minutes. Let's see, the solution was 4484.349 seconds. This is the time required from the start. This is the total time required from the start. Total time required from the start of the readings. First time, that is from time t equals to 0. Okay, let's take the same problem, but we're going to take from reading number 2. We want to say how much more time it's needed now to reach to the level of 10 centimeters, but from the level of h2 45 centimeters. So I would say from 45 centimeter to 10 centimeters, how much time I need to go. I need how much time from reaching to the level of 10 centimeters, but from the 45 centimeters. I can write the equation again, that I need the time t from, I can write t from h equals to 45 centimeters. From 45 centimeter height, from that height I'm going to take some time to reach to the value of t equals to 10 centimeters. Okay, so for that I would write ln of your height is from 45 centimeters to this height of h6, and this is equals to 10 centimeters, and this is equals to 1 by time. Initial value of time was given to us, that was 12 minutes. 12 minutes was given to us, and in the interval of ln of 60 by 45. So from that I can get the value of time t equals to how much? 3764.3490 seconds. That is how much minutes? 62.73 minutes. So that is lesser than the previous case because we have already calculated 12 minutes. We have already taken the 12 minutes in that part. So if we try to add that 12 minutes also, you would get the initial value of that time. What was the total time required? So that was one more solution. You can check that out. I would write that. If you try to multiply that, if you try to add this 12 minutes in this equation, you would see how much is the value. Let me check. So we have this 3764.3490 plus 12 minutes. That's 12 into 60. So that's 4484.349 seconds. It is similar to that of a previous case when we said that I want to go from time t equals to 0 to time t such that my level was initially from 65 to 60 to 10 centimeters. So that's all about that final problem of that variable head method. Thank you for watching. I would say thank you for watching our method of permeability of test, calculation of coefficient of permeability of test using the lab methods. Thank you. Okay.